Okay. All right, so we're going to finish chapter 38. The remaining concept are Schrodinger's equation, Heisenberg's uncertainty principle, and also tunneling effect. So yesterday we mentioned that all the subatomic particles like electron, protons, and photons, they all behave. They are governed by the Schrodinger's equation, and the wave function is the solution to the Schrodinger's equation. Okay, so the wave function is this. So C, the capitalized C, is a function of position and time. And in this case, we can actually separate the time and space into the lowercase c, which is just a function of position, and then times the time-dependent part, which is e to the minus I omega t. Omega is the angular frequency. Okay, and so this is the solution to the Schrodinger's equation. We call this wave function. And wave function itself is what we call the probability wave. It is not physically detectable. So, but the wave function square, or the absolute value of wave function square, is what we call probability density, and it has physical meaning. Okay, and it describes the probability of finding the particle at certain location and time. Now, what is the Schrodinger's equation? So Schrodinger's equation, let's see, if we're just looking at the most simplified case, which is one-dimensional and time-independent. So if you're dealing with a one-dimensional time-independent Schrodinger's equation, then the equation is this. So it's a second-order differential equation. So d squared c dx squared, because we're dealing with one-dimensional case. And then plus, you have number 8 times pi squared, and then times the mass of the particle, and over the Planck constant square, and then times the total energy of the system minus the potential of the system. And the potential usually is a function of position. And then times the wave function again, c. So that whole thing is equal to 0. So this equation described, this is the one-dimensional time-independent Schrodinger's equation. And so you have this second-order differential equation. Now, in order to see what the so we can use Schrodinger's equation to describe how the particle behave. So let's say you have an electron. So let's say you have an electron that's coming from the left and it's moving in this direction. And there's no force acting on the electron. So let's say this electron is a free particle. When we say it's a free particle, it means that there's no force acting on it. When there's no force acting on the particle, then the potential energy of the particle can be set to 0. So in other words, for a free particle, there's no potential energy, because potential energy and force are tied together. Because there's no force, so there's no potential energy. Okay, so in this case, this equation can be written down as this. So you have d squared c dx squared, and then plus all these things in front of the brackets, and then h squared, and then times the energy of the system, and then times the wave function, and then there's no potential energy, and the whole thing is 0. Okay, now because there's no potential energy, so then we can say that the energy of the system is just simply equal to the kinetic energy of the system, because there's no potential. Because mechanical energy is equal to kinetic energy plus the potential energy. When now there's no potential energy, then your E is equal to the K, which is the kinetic energy. And then we know that kinetic energy is equal to 1/2 mass of the particle, and then times the velocity squared. Okay, and we further know that the linear momentum is equal to mass times velocity. So in this case, your energy of the system can be expressed by momentum, because if you take square of this equation on both sides, so then you have square it, you square it, and you square it, and then express the v square, in terms of p and m, then your total energy of the system is simply 1/2, and then times mass in the denominator, and in the numerator you have that p squared. Okay, so this relates the linear momentum to the total energy of the system when there's no potential energy. So your total energy is p squared over 2 times the mass of the particle. Then we're going to replace this E with that expression. So then what we have here is that you have d squared c dx squared, and then plus a times pi squared times mass over your h squared, and then your E is represented by p squared over 2m, and then times c, and the whole thing is 0. So you can see that your m here cancelled, and your 2, you have 8 in the numerator, you have 2 in the denominator, that becomes 4. So this equation becomes 4 pi squared p squared over h squared. So turn to the next page, then this equation now can be written as, you have 4 pi squared p squared over the h squared, and then this. That's equal to 0. So we can rearrange this. So you have your d squared, and then dx squared, and then plus. So let's say you have 2 pi, and then you have your p, and then you have your h, all within the parentheses, and square it. Okay, now if we look at this, we can definitely identify that, if you recall, any momentum, electrons or any subatomic, particles, their momentum can be is related to their wavelength, which is called the Broglie wavelength, and your p is equal to h over lambda. So in this case, when you have p over h, that just give you 1 over lambda. And what does that mean? It means that this can further written, represented by the wavelength. So you have this, and then you plus. So this becomes 2 pi over lambda square root and times the wave function. Now, if you recall, 2 pi over lambda is basically the wave number. So your K, this is not Canadian energy, this is wave number. So wave number is 2 pi over lambda. And so this equation can further be written as this, and then plus K squared wave function, and then equals to 0. So what kind of equation is this? We start out with the Schrödinger's equation, and you have involves the energy and potential because we're dealing with a free particle, so that there's no potential energy. And then based on the the relationship between momentum and kinetic energy, and also the relationship between momentum and the wavelength, the wave number. What we got here is this equation. This is a second order differential equation. There's no source here. And the equation, if you know your math well enough, you know that the solution to this equation is simply c as a function of x, that is equal to a constant times e to the ikx, and then plus I, which is the complex number, and then There's no I here. Okay, plus b, and then e to the minus ikx. Okay, so the first term, this term describes the incident wave, and this term describes reflected wave. So one is leftward and one is one is rightward and one is leftward. Okay, so this is the full solution to the first order one-dimensional equations, and this is the time independent part. So to have the complete solution, then you will multiply this by e to the minus I omega t to give you the time-dependent solution for one-dimensional case. Now, because we're dealing with a free particle, so when we say a free particle, and then we're dealing with a forward a rightward moving particle, so you can set b equals 0, and we can further let a to be a constant. So this is just the amplitude of the wave, and let's say is c sub 0. So the solution now becomes the time independent part is a constant, and then times e to the ikx. Okay, so like I said, this is a solution to the Schrödinger's equation. This is a wave function, which is a probability y. But then probability wave itself is a complex number. It has no physical meaning. So in order to know, in order to know what is the probability of finding the electron at certain location, you have to calculate the probability density. So what is probability density? Probability density is simply the wave function squared. So if you have this, you square it. So we do this, so you have the constant, you square it. And then when you have the EIKX, when you square it, basically you're multiplying this and then e to the minus IKX. So the IKX and times the minus IKX, that just give you 1. So this whole thing becomes this. So what does that mean? When you calculate, after you solve the equations, after you calculate probability density, which is a constant. And it just means that the electron, there's no preferred location for the electron to be. The electron can be anywhere. So if you plot the wave function, so let's say this is the probability density as a function of position, you'll find that the particle can be anywhere because it is a constant. It has no preferred direction. Okay, and that ties to the next concept, which is the Heisenberg's uncertainty principle. But this just tells you that when we're dealing with a free particle, you can you can use Schrödinger's equation to find the probability of finding an electron. And in this case, we found that the probability is a constant, and the probability density is a constant, which means that there's no preferred direction for the electron to be. It can be anywhere. Okay. Now, the next concept we want to talk about is the uncertainty principle, which is proposed by Heisenberg. So what does Heisenberg's uncertainty principle entail? Okay, so uncertainty principle. It basically just means that what it means is both the position and the momentum cannot be measured with unlimited precision. They are always the product of these two quantities is always subject to some sort of uncertainty. So in terms of math, it means that the uncertainty in position times the uncertainty in the linear momentum in that direction has to be greater or equal to a number, and that number we call the h bar. And what is your h bar? H bar is basically h over 2 pi. We define that to be h bar. Okay. So in other words, if you know the positions, or if you know precisely the positions of the of a particle, you cannot know. You have no you don't know what the momentum is, because when the delta x is 0, then the delta the uncertainty in the linear momentum has to be infinity, so that the product will be greater than a constant, h bar. Okay, so this equation describes the uncertainty principle applied in the horizontal direction. If you're talking about, if you go up to three dimensions, then you have delta y times delta p x p sub y that has to be greater than h bar, or delta z times delta p sub z that has to be greater than h bar. So in other words, the product will be the uncertainty of the position in that direction times the uncertainty of the momentum in that direction. You do not have a term that's delta x times delta p sub y, or delta x times delta p sub z. It has to be in the same direction. There's also another equation that follows the uncertainty principle in terms of the energy and time, and that is delta E, the change in energy, or the uncertainty in energy, and the uncertainty in time has to be greater than h bar. Okay, so that is that. So if we apply Heisenberg's uncertainty principle to the free particle case that we just mentioned, so what we have here is that you have a free particle that's moving, that is not under any force, and it can move anywhere. So which means that in this case we know the linear momentum precisely, which means that your delta p is 0 in the x direction. And if that's the case, then from Heisenberg's uncertainty principle, then delta x has to be approaching to infinity, so that the product of this and this will still be greater than h bar, because 0 times infinity is not 0, it's not infinity, it's actually will be a number. So the product of this two will be greater than a number. Okay, and that's because when we have a free particle, and when we know with a precision, when we know there's no uncertainty in the momentum, then which means that there's a lot of uncertainty in its position, and that's what what this constant means, because there's no preferred location for the electron to be, so your delta x basically is like approaching to infinity. Okay, now the final concept that we want to talk about is tunneling effects. So what is tunneling effect? Now tunneling effect is basically a quantum mechanical effect. This things does not happen in classical physics, and that is because if it happens, then it will violate the conservation of energy, just by the apparent look. Okay, so let's say you have an electron or any subatomic particles, and let's draw it like this is in the horizontal direction, this is positioned, and in the vertical direction, that's the energy. Let's say you have an electron that's coming from the left and it's moving in that direction. Let's say in front of it you place a potential wall or a barrier, and that potential has, let's say, this amount, and on the vertical that's energy. Okay, energy level, and so within this barrier it has the potential, let's say this one. Okay, so now classically this is so everything is drawn to scale. So this is the energy of the electron, which is, you can see that it's under the potential of the barrier. So if electron, so is it possible for the electron to appear inside or outside, or on the other side of the barrier? Classically it is impossible, because if you look at this, you have total energy of the system of the electron that must be equal to the kinetic energy of the electron plus the potential that the electron experiences. So within region 1, the electron is considered as a free particle, so there's no there is no so you have your there's no potential, so the energy is entirely in the kinetic energy. Now within in this region too, which is within the barrier from 0 to L, okay, if you look at this, your energy your energy itself is already less than. So if you rearrange this, your energy your energy is less than the potential of the barrier. So on the left hand side, you will get a negative value because E is less than U naught, which means that your K, the kinetic energy of the electron, must be less than 0. However, our kinetic energy is equal to 1/2 mv squared. You cannot have a something that's squared that's a negative value, because then your velocity will be a complex number which does not exist in our real physical world. So which means that classically you do not expect electron to appear within region 2, and this cannot if it cannot appear in region 2, there's the electron cannot be in region 3 because it has to pass region 2 in order to reach region 3. So classically, that picture just shows that electron can only move in region 1. It cannot be observed in region 2 or 3. But quantum mechanically, what's happening is that you do not treat electron as a particle. You treat it as a wave. So as a wave, somehow it can wiggle through its wave through this barrier and appear on the other side of the barrier in region either 2 or 3. So you can actually use the Schrodinger's equation, and then now your potential is not 0 anymore, because now within region 2 it experience the potential. So you can use that equation and then solve for the solution. And once you have the solution, you can calculate the probability density. And so the probability density basically is like this. So again, this is on the horizontal, that's the position. And on the vertical, that's the probability density squared, the probability density. Okay, so this is from 0, and this is L. This is the the region of the barrier. So what we found is that before the electron encounter the barrier, it will behave like a wave, just like the free particle. And for the free particle, if you remember, we have the e to the ikx as a solution. So it will oscillate like this. So the wave function will actually like this. And then once you encounter this barrier, you'll find that classically your probability density will be 0 because it cannot appear within region 2 and 3. But quantum mechanically, we found that it is non-zero, and it actually has some sort of like this. So this just tells you that it's non-zero. Probably there's a finite chance, finite probability for the electron to appear on the other side of the barrier, not 0. Okay, so that's a drastic difference between the classical view and the quantum mechanical view. And this is what we call the tunneling effect. And in fact, our computer use a lot of tunneling effects because all the electrons, within this, the keyboards. If you read the text, you'll find that the keyboards has a lot of a tiny potential barrier, and the electron actually has to tunnel through so that it can be, current can be formed and stuff. Okay, and that's just using the tunneling effects. Okay. So these are the three remaining, so we pretty much officially, finished chapter 38. Now we're going to do some problems. Okay, so the first problem we want to do is problem 29 from chapter 38. Okay, we're doing 29. So that's on page 1080. So we're doing this problem chapter 38, problems 29. Okay, so the problem reads, What frequency and photon energy and photon momentum magnitude in kilo eV per C are associated with X-ray having wavelength that's 35 picometers. So in this equation, in this problem, the wavelength of a photon or the X-ray is given, which is 35 picometers, and pico is 10 to the negative 12. So we can just express that in terms of SI units. And you're asked to find the frequency of the photon. You're asked to find the energy of the photon and linear momentum. Okay, so how do we do this? And so we're going to use everything in, let's see. So for frequency, it's easy because once you have the wavelength, remember the energy of a photon is equal to HF, and frequency and wavelength are related. And let's see. Okay, that's for Poppy. So we want to do frequency first. So how to calculate frequency? We know that frequency and wavelength are related by this. Okay, it's the speed of light over the wavelength when you're dealing with a photon. So in this case, the speed of light is 3 times 10 to the 8th, and the wavelength is 35 times 10 to the negative 12. So when you just plug in, and that's easy to do. So when you do that, you'll get a frequency that's very high. It's 8.57 times 10 to the 18 hertz. That's the frequency. Okay, and that's in hertz. And the second part is you want to calculate the energy. So energy and frequency are related. So E is equal to HF. So, and I think in the book, if you use, let's see, so you can either use the SI unit or use the KEV, the EV units. So let's see, if we use the EV units, then the Planck constant is 4.136 times 10 to the negative 15, and that's in EV times second. And then you times the frequency, which is 8.57 times 10 to the 18. Then you'll get your energy of the photon, which is 3.55 times 10 to the 4th, and that's in EV. Okay. And personally, I would prefer everything to be expressed in SI unit so that you don't get confused. And then the conversion between the SI unit and the EV is very easy to do. So if you have this amount in EV, then just multiply this number by 1.6 times 10 to the negative 19. That will convert it to joules, and you can do that later. So the last part is that you want to calculate momentum of the photon. Now, momentum of the photon is easy to do because if you remember, that will be just h over lambda or E over c. Now we're not going to use E over c because I did not calculate energy in joules. So that just use h over lambda, and your h is this number. This is in joules, 6.626 times 10 to the negative 34, and then over the wavelength. Your wavelength is 35 times 10 to the negative 12. And so when you do the calculation, you get that the linear momentum of the photon would be 1.89, and then times 10 to the negative 23rd, and the unit for linear momentum is kilograms times times meters over seconds. Okay, so that's the first problem. It's easy to do. When you're given the wavelength of a photon, you can use that information to calculate the energy of the photon, the linear momentum of the photon, and the frequency of the photon. And the next one we want to do is the Compton's Compton's effect, which is problem 40. Okay, so problem 40 says, what is the maximum kinetic energy of electrons knocked out of a thin copper foil by Compton scattering over incident beams of 17.5 kilo eV X-rays? Assume the work function is negligible. All right, so now we have a Compton effect. So let's draw the picture. You have a target right here, and you have incoming, photons with the let's see, wavelength is not given. Let's just associate that with lambda, and the energy is given. The energy is 17.5 kilo eV, so 17.5 keV, and you're asked to find after the collisions. This is a Compton effect. So a Compton scattering after collision, we'd expect that there's an outgoing photon with a different uh, wavelength, and of course with a different energy, and there's a outgoing electron, and that electron will have some kinetic energy. And then you ask to find what is the maximum kinetic energy that the electron can obtain after the collision. So how do we do this kind of problem? So this is basically everything is conserved, conservation of energy. So you can write down that the energy of incoming photon has to be equal to the energy of outgoing photon, E prime, and then plus the kinetic energy of the electron. So in order for this, for this to be maximum, then we have to make sure that this becomes as smallest as possible. Okay, so how do we ensure that this is smallest? If the E prime is smallest, which means that if you recall, energy and wavelength are proportional inversely. So if E prime has to be smallest, which means that the wavelength change has to be largest. So in other words, your delta lambda, the Compton shift, has to be largest in order for the outgoing photon to have the smallest energy possible. Okay, so what is Compton defect? So let's write down the Compton wavelength, Compton shift. Your delta lambda is equal to the outgoing wavelength minus incoming wavelength. In addition to that, that's also equal to the H over MC, and then 1 minus cosine phi. Okay, so in this case, we can calculate the incoming wavelength because energy is given. However, we do not have the information of outgoing energy. So, and that is something we need to infer from information that we're given. Because we want to find the smallest E prime, which means that lambda prime has to be largest. In order for lambda prime to be largest, it means that your delta lambda, the Compton shift, has to be largest as well. Now, if you look at the phi, the angle phi, your angle phi has to be at 180 degrees, so that your delta lambda will be the largest. So if you choose phi to be 180 degrees, which means that your delta lambda, the Compton shift, is basically equal to 1 minus 1, so that becomes 2h over mass of the electron, and then times the speed of light. So in other words, in order for the kinetic energy to be kinetic energy of the electron to be the maximum, then the outgoing photon has to have the smallest energy. For the outgoing photon to have the smallest energy, the Compton shift has to be largest. So for the largest Compton shift, your phi, the angle, has to be 180 degrees. So that becomes 2 times the Compton shifts. Okay, two times the Compton wavelength. So now we deduce that so what is our lambda prime? To calculate lambda prime, we need to calculate our lambda first. So our lambda, if you remember, our lambda would simply be it is related to our energy. So our lambda is equal to hc over the energy of the photon. Okay, because E is equal to hc over lambda. So if you plug in the numbers, your h, you use let's see. Okay, we can use the EV notation. So you have 4.136, and then times 10 to the negative 15. This this is a Planck constant, in terms, in units of eV times seconds, and then times the speed of light, which is in SI unit. Okay, so you might say, okay, we are mixing two different units together, but that is okay because we have in the new denominator, the energy is expressed in EV, so that EV and EV cancel. So what's left is in SI unit. So you have 17.5. You have KeV, so remove times 10 to the third. So this is in EV and H is the EV, so everything cancel out. And what you have here is that your wavelength is equal to 7.09, and then times 10 to the negative 11, and that will be in meters because everything is SI units. Okay, and the EV and EV cancel. And now, so once we have that, then we can calculate our delta lambda. What is our delta lambda? Our delta lambda is equal to 2 times. So here the H I'm going to use the SI unit. So that you have 6.62 times 10 to the negative 34, and then over the mass of the electron, which is 9.11 times 10 to negative 31, and then times speed of light times 3 times 10 to the 8. Now, you might wonder why did I use a different Planck constant? Because if you look at this in the numerator, in the numerator you have the Planck constant. In the denominator you have the mass of electron, which in in SI unit, and C is also in SI unit. You do not have the corresponding EV, so you cannot use the Planck constant EV. You have to use Planck constant in joules, so that way everything will be consistent in SI units. So you don't have that after you plug in the numbers, you'll get this number. That'll be 4.85 times 10 to the negative 12, and that's in meters. So once we calculate our delta lambda, then the outgoing wavelength can be calculated because the definition of delta lambda is the lambda prime minus lambda. So your lambda prime is basically the original or the incoming wavelength plus the Compton shift. So when you do the calculation, when you add this together, your outgoing wavelength is 7.575 times 10 to the negative 11 meters. Okay. All right. So now we figure out the outgoing wavelength. In that case, we can use that information to infer to calculate the energy associated with that photon. So your E prime, the outgoing energy of the photon, is equal to hc over lambda prime. So you just plug in a number. So again, because the energy are expressed in EV, so my H here, I'm going to use the number that's in that is in EV. So when you do the calculation, you kind of have to be careful which H to use. Now, if you think that there's just too much trouble to remember, then just use everything in SI unit, which means that energy has to be in joules. That will be acceptable as well. Okay, and your H prime here, your lambda prime is we just calculated. You just plug in. And so the energy of outgoing photon will have this value. That will be 16 and then 16 kilojoules. So that will be 16.379 keV, because the incoming is expressed in keV. So outgoing is also in keV. So now what will be the maximum kinetic energy of the electron? If you remember, the E is equal to E prime plus K. So we just plug in whatever number that we have. So your E, the incoming photon has 7.5 keV, and your outgoing photon has 16.379 379 keV. So what's left is picked up by the electron. So the electron has the maximum kinetic energy of the electron in this case would be at 1.121 keV. Okay? So if you do not like the unit of EV, then just use everything in SI unit. That will do. Okay? And the next problem that we want to discuss is problem 55. Okay, so problem 55. If the de Broglie wavelength of a photon is 100 femtometer, what is the speed of the photon, and through what electric potential will the photon have to be accelerated to acquire this speed? Okay, so the wavelength of a photon is given, of a proton. Okay, the wavelength of proton is given, which is 100 femtometer. Femto is 10 to negative, so it's 100 and then times 10 to negative 14 meters. This is a proton, okay? And so we call that wavelength the de Broglie wavelength. What is the speed of protons and through what electric potential? So you want to find the speed, the velocity, and the electric potential. The electric potential we use capital V to indicate. So one is the speed, one is the electric potential that the proton has to be accelerated to acquire this speed. Alright, so you're just giving the information the wavelength, and it seems like you can use that information to calculate your velocity and the electric potential that is required to accelerate the proton to have this kind of wavelength. Where do we start? Okay, since we're talking about the wavelength, you can actually associate, remember, for every de Broglie wavelength, there's a linear momentum associated with that, and linear momentum is h over lambda. So you have the wavelength. So you can calculate the linear momentum. Okay, and the linear momentum is also equal to the mass of the particle times velocity, and that's how we relate the wavelength to the velocity. So we can plug in the numbers. So h is 6.625 times 10 to the negative 34 over the wavelength, which is 100 times 10 to the negative 15, and that must be equal to the mass of the proton. Now it's not the mass of the electron, so the mass of proton is 1. You can look it up in the back of the book. It's 1.67 times 10 to the negative 27 kilograms, and then times the velocity. So from this, you can calculate your velocity, and that velocity is equal to 3.96 times 10 to the 6 meter per second. So this is how fast the proton will move. Now, through what potential? Through what electrical potential would this proton be accelerated? Now remember, the electrical potential is U, and that's equal to the charge of the particle times the potential difference, and that must be equal to the kinetic energy, because that's how the proton is being accelerated, because the energy comes from the electrical potential energy and turn into the kinetic energy. So the electrical potential energy is Q times V, and that's equal to 1/2 mass of the proton and then velocity squared. So in this case, your potential, electrical potential, is simply equal to mass of the proton times velocity squared and then over 2 times q. Okay, and the charge of a proton is the same charge as the electron. So when you plug in the numbers, so you have the mass of a proton is 1.67 times 10 to the negative 27, and then times the velocity square, which I'm this, whatever this, you square it. I'm just going to write it. Yeah, you square it, and you divide it by 2 times the charge, which is 1.6 times 10 to the negative 19. And so once you do the calculation, your answer will be 81.8, and then that will be in kilovolts. Okay, so it's 81.8 times 10 times 1,000 volts. All right. So you can see that once you know the wavelength, you pretty much know everything else: the linear momentum, the frequency, the total energy of the system, and stuff. Now the last problems I want to do is problem 81 that deal with the uncertainty principle. So 81. So imagine playing baseball in the universe, not ours, where the Planck constant is 0.6 joules. So joules times seconds, and thus quantum physics affects macroscopic objects. What would be the uncertainty in the position of a 0.5 kilograms baseball that is moving at 20 meters per second along an axis if the uncertainty in the speed is 1 meter per second? Okay, so in other words, let's say in a different universe, they have a different Planck constant. And then, so what would be, and then regardless, the Planck constant value is uncertainty principle applies. So let's just write down what we have, what given. The Planck constant now is 0.6, and that's in units of joules times seconds. And the mass of the baseball is 0.5 kilogram. And the velocity of the ball is 20 meters per second with the uncertainty that is 1 meter per second. So in this case, we will express that as delta V, that's 1 meter per second. Okay, and you're asked to find what will be the uncertainty in position. So remember, what is the uncertainty principle? It is delta x times delta px, p sub x, that has to be greater than h over 2 pi, which is h bar. So in this case, your task is to find what delta x has to be. So we said that, delta x at least has to be equal or greater than your h bar, or h over 2 pi, and then over the uncertainty in linear momentum. So what is the uncertainty in linear momentum? The uncertainty of the linear momentum would be, you have the velocity p is equal to mv. So in this case, your delta p is equal to m delta v. So when you plug in the numbers, so your m is 0.5, and your delta v is 1, and your h now is in a different universe, that's 0.6. So when you plug in those numbers, 2 pi, and then you have 0.5 here, you will get the uncertainty of the position to be around 0.19 meters. So I think if we want to be rigorous, I think we need to keep that greater sign. So it's greater, and that's equal. So your delta x has to be greater or equal 0.19 meters. Okay, so that's basically it. I'm going to stop the recording.